Oh, there we go. All right, so you should be able to see my screen. This is just a quick Castle Learning rundown. If you just need to pause and see the equation or anything, you kind of just skip through. You see for all the questions, there'll be the question up here, and then the answer, and then the equation. So I know the main difference here is they write the equation out, then they rearrange. So the left side is just the variable they're looking for, and then they substitute in, which is totally fine. Just know a lot of people don't do that. Um, but anyway, I'll show you how they get the equation. So this should hopefully go quicker since there's 24 questions. But you have a spring, the spring constant, so you'd write K equals 68 newtons, hanging from the ceiling, and then a 12 Newton downward force. So again, your two main equations are about force and about potential energy. So as soon as you, 99% of the time, as soon as you see they even just mention a force being applied to the spring, that means you have to use Hooke's law right down here, which is the force of a spring equals K times X. And then, of course, they ask for how far it's stretched, which is a distance. So you know the force is 12, so 12 equals 68 times X. So you're just doing 12 divided by 68. Get your answer. Question 2. This one's a little different. So they say your length of the spring is 0.4 when it's unstretched, and then they add a 10 Newton weight, and it stretches all the way out to 0.6. So now the tricky part here is X in your equation, same equation as before, is not 4 or 0.4 or 0.6. It's the difference between the two. So it's 0.2, and you can see that's substituted in for X. And then 10 newtons, again, and you're solving for the spring constant there on question 2. Question 3, here's the difference now. See, they mentioned joules, and joules is energy. So they're still talking about a spring constant. And note at the bottom here, the equation has changed. So before in the last one, they wanted spring constant K, but we used F and X. But now because they give us the joules, that's an energy. So we're going to use the energy stored in a spring equals 1/2 K times X. You can substitute X in as 0.2, 10 in as your potential energy, and you get your answer right there for your spring constant. Question 4. All right. So let's see. So a compressed spring. The thing that threw me here is this is grams. We don't want grams. We're going to want kilograms. So you got to move it 3 places to the left. 1, 2, 3. So it's 0.005. And then they give you a speed. So they want the amount of potential energy, and they wrote it out right here. Good, we want our potential, but to find our potential, we have to use our kinetic, because energy is always conserved and can be transformed from one form to another. So we're just using the kinetic energy equation to solve, because we know the kinetic energy will be transformed into potential. So they give us the speed. We can plug that in for V. The mass, we just got to convert it, so it's 0.005 and then divide by 2. That's where the 0.5 came from. Answer should be choice 3. Question 5. Love a good graph question. Which graph best represents the relationship between the potential energy stored in a spring and the change in the spring's length? So looking at the equation, potential energy of a spring equals 1/2 K X squared. So PE is on the y-axis. 1/2 and K are both constants, so just a number. And then X is on the x-axis. So this is really like a y equals a constant times an x squared. So that's why it looks like choice 1 here, because it's a y equals x squared relationship, and that's choice 1 is what that graph would look like. Question 6, a vertical spring has a spring constant. All right, so they gave us K equals 100. Tension spring changes from an unstretched length of 0.5 to 0.65. So this is, I think, similar to question 2. So you're not going to use either of those numbers. You're going to use the change. Oh, my light's timed out. So that's why the distance here is 0.15. So you get 15 newtons. Question 7. When a mass is placed on a spring with a spring constant of 60 newtons, the spring is all right, and they want a compressed, and they want energy. So again, they're giving you a spring constant, they're giving you a distance, but you got to just key into what are they giving you here, and that's energy. So we use the equation down here for energy. And then we just substitute right in, make sure you're square, do your math right, you get 7.5. I feel like I'm going to sneeze. I'm going to try not to. You gain 2.34 joules of elastic potential energy as it's compressed. What's its spring constant? All right, they give us energy, they gave us distance, they want spring constant again. Here it is, energy in a spring. You're coming back to that equation, substitute in for potential and for x, and you get almost 75 newtons per meter. Question 9. Oh, they got a diagram here. So which statement best describes the transformation of energy that occurs? All right, so we wind it up, it moves, and then it stops. So their explanation, no, that's their reason, is conservation of energy. So the elastic, it looks like it's choice 3. The elastic potential energy, that's the spring energy, because elastic spring energy is the same, becomes kinetic. So you wind it up, that's the elastic. Then it moves, that's the kinetic. And then it's converted into internal energy. That's because it stopped. And internal energy, we missed this on the last quiz. Remember, it's just your friction. So it stops because of friction. Question 10. A spring with a spring constant of 4 newtons per meter is compressed by a force. So what is the total elastic potential energy stored in this? So this is a two-stepper here. So the first thing we need to do is use Hooke's law to use the force and the constant to get the distance. And then we can use the spring constant and the distance we just found, that's where the 0.3 comes from, to plug into the energy equation. Very good. I assume most people found the value of the number and then substituted it in, but you could rearrange and redefine x as Fs over k and substitute that in. 18 joules. Question 10 is tricky, 2 steps. A child has does 0.2 joules of work. So joules is energy, work is change in energy. And they give you the mass of the toy. What's the maximum vertical height? So this is another one here. We're talking about energy and we're talking about a spring toy, but you're talking about what height is it going to reach. So you can press it. So that's setting the amount of energy as spring energy. You release it, it becomes kinetic, and then it loses its kinetic when it finally gains gravitational potential. So again, we're just talking energy conservation, energy transformation here. So the total amount of energy is 0.2, but we're going to use our gravitational potential energy for that, our GPE. So you know M, they give it to you. You know G, of course, is 9.81. They use 9.8. It's old. And then you solve for your height of 2 meters there. All because of energy conservation and transformation. Question 12. Decreasing gravitational potential energy, wild card here. So a girl stretching a spring, that would be increasing spring potential. Bicyclist riding uphill is increasing your height, so that's not decreasing your potential. A rocket rising vertically, again, increasing your height. And then a boy jumping down from a tree. So this is the only one where we're losing height. So that's why it's choice 4. All right, halfway done. I like this one. So the diagram below shows a toy with 16 joules of kinetic energy traveling on a frictionless horizontal surface towards a horizontal spring. If the car comes to rest after compressing the spring 1 meter, what's the spring constant? So this is similar to question 11. We're talking conservation of energy, energy transformation. So yes, it says kinetic energy, but we know at the end that's going to all be stored and converted to spring potential energy. So 16 joules is what we're using for your spring potential. The 1 meter is x, and then you could solve for k using your spring potential energy equation. You get 32. Question 14. Derive the spring constant in terms of m, x, and v. Ooh, I like this one. So spring toy cars compress distance x when it's released, transferring energy, and has mass m and speed v. So again, energy transformation and conservation. So your energy is transformed from potential in a spring to kinetic. So that's why we're setting those equal to each other, because it's conserved, so they're the same. And then you just write the equations out and rearrange. So the 1/2 is on both sides, so you could cross it out. And then you just divide by x squared, and you get it. This seems tricky, but I bet if I gave you all the values, if I told you what the values were for those variables, you would just solve it, no problem. It's funny how that works out. This is like question 2, it seems. So we have a 5 Newton book, that's a force. And it shows how much it stretches from its initial to its final position. What's the spring constant? We're talking Hooke's law again. just doing some simple division once we substitute the force and the distance. All right, then a spring constant. Oh man, I'm sorry for that pause. I just felt like I don't even know if it's definitely recording. I don't see a recording symbol somewhere. So, I mean, if it's not, you'll never see this, but hopefully it is. Spring constant of 80, a displacement of 0.3, the potential energy. Should be very used to this. It's like taking free throws now. So potential energy of a spring, that's the equation we're using. 1/2 kx, they give us k, they give us x. Plug in, don't forget to square. 3.6. I like this one. This has to do with your lab. This is your Hooke's Law lab. You had to make the slope and identify what it means. So you should know that the slope is the spring constant. So the one with the, oh, here it is, the greatest. I was looking for the actual question, is the steepest one. So it's A, and again, that's just like the lab you did, made a graph. When a mass is placed on a spring constant of 15, so we know K is 15. It's compressed 0.25, so we know X, how much potential energy. All right, we know K, we know X, we want energy, plug right in, 0.47 joules, don't forget to square it. Question 19, a vertical spring of 0.1 meters is elongated. All right, so this is like question 2. We're not using either length, we're using the change, so 0.019. And they give us the mass, and they want the spring constant. Oh, okay, so this one adds a new fold, a little new wrinkle here. So the first one is they give us a mass, but we need a force. So you actually, this is exactly what you did in the lab. They gave you the mass, actually in grams, and then you had to convert to kilograms, and then you multiply by 9.81 to get the force. So you do that, so you don't have to convert to kilograms, at least this time, but you do 1 kilogram times 9.81 meters per second. That gets you your force. And they gave you the distance of 0.019, and that's how you get it. Very good. Question 19, final 5 questions. A 1.53 kilogram mass is placed on a spring with a spring constant of 30 newtons per meter. It's compressed 0.5. How much energy is stored? So this is one of the examples where they give you extra stuff. You don't actually need the mass. They give you the spring constant and the distance. So spring constant and distance to get energy, plug right in. You get unit amount of joules. Question 21. Spring scale is produced by in the produce department of a supermarket stretches 0.025 meters when a watermelon. Oh, the huge scientific notation. If you don't know what that means, just plug it into your calculator. 1 times 10 to the second. So that's newtons. That's a force. This is a K value, this is a distance. They want the K value, so we're using Hooke's Law again. Force divided by X, get K. Yep. All right, last 3. We start at 0.5, we go to 1, so our distance we stretched is 0.5. 15 joules of energy, what's the spring constant? All right, they gave us energy, they want K, we know X. Substitute in. Here they show you how they came up with X. It's good. Get your answer. Last 2 questions. Oh, an apple falling from a tree onto a spring. Newton would be so proud. It hits the spring. It compresses at 0.1 meters from its rest position. What is the spring constant? All right. So here. All right, so this is similar. I'm trying to think of the question. I don't remember it. It was the one with the wind-up toy that hit a spring. So instead of having your kinetic energy become spring potential, you're having your gravitational potential become spring potential. Or it's like the other one that you push the toy down, then it popped and went up. It's just playing that backwards. So it's up. So it's gravitational potential, mgh. It falls down, gains kinetic, loses the kinetic when it hits the spring and pushes the spring down. So you have mgh, that's your total energy. I would probably just solve mgh. Do they give you h? Yeah, 2 meters, mass of 0.1, g is 9.81. I'd probably just solve that and then take that number and set it equal to 1/2 kx squared. But here they just substituted mg and h straight in and then plugged it all in. And then the last one here, compared to the spring constant for A, the spring constant for B is greater, larger. And this again is the, oh, sorry, yeah, they flipped this. B is larger. You're like, wait, it doesn't have as much of a slope, but that's because they put force on the x-axis. We did it the other way. So take the graph and rotate it like this. Yeah. All right. So again, it has more force per distance. That's what you're looking at. All right. That's it. I hope this recorded. And I will hit pause. And have a good one. Like and subscribe. Hope you enjoy it.